Hello again. So now we're going to take the idea of the rate of change and we're going to build on it, because what we've seen is that this idea of the slope of a secant line to the tangent line, or the average velocity to the instantaneous velocity, we've seen that those are really the same concept, just with maybe a different type of function. This idea that these same two problems, these have the same concept behind them, leads to an important idea in the building of the calculus, and it's called the derivative. So let's review our notation, look at a couple problems, and build a new concept and a new notation for it. Alright, so here's what we've said so far. If we have our generic curve f of x, our generic function, then if we wanted to find the slope of a secant line over to the function f of x over some interval a to x, where x is just some general value. Alright, so here we have a, and here's some general point on the curve defined by x. Remember that this point would be a f of a, and the second point on the curve would be x f of x. Then the slope of the secant line, right? So if we were to connect those 2 points, the slope of the secant line is then given by f of x minus f of a over x minus a. That's the average rate of change. Now, if we wanted the slope of the tangent line at A, so the slope of the tangent line says, okay, now at A, then remember the tangent line just hits the curve at that point. It just sort of glances off at that point. And what we've seen is that the slope of this tangent line is an instantaneous rate of change. And one way we can express it is as the limit as x approaches A of that average rate of change, f of x minus f of a over x minus a. And I say if it exists, because this limit may not exist. We've seen situations where in calculating a limit we may not get the same values on the left and the right, so the limit may not exist. Alright, so what we say that this instantaneous rate of change, if it exists, is the slope of the tangent line. Alright, so let's use that notation and see an example. Let's find the equation of the tangent line to f of x equals x cubed at x equals 4. Alright, so if at x equals 4, that means that my a value is 4. Right, at x equals 4. So then I can think of this, if we want the equation of the tangent line, I need the slope of the tangent line first. Let's find the slope. The slope is the instantaneous rate of change. And so that's the limit with x approaching 4 of f of x minus f of 4 over x minus 4. And so then that's the limit with x approaching 4. Now f of x is x cubed. F of 4 is 4 cubed, which is 64, over x minus 4. Now we cannot directly substitute here. Since x cubed, if x approached 4, that would be 64. We have 64 minus 64 in the numerator. 4 minus 4 in the denominator, we have 0 over 0. It's an indeterminate form. So we have to use some factoring tricks here. Now, if you weren't aware, this is this form, this x cubed minus 64. That's called a difference of cubes. In general, the pattern for the difference of cubes, a cubed minus b cubed, is a minus b by a squared plus ab plus b squared. And if this were a plus instead of a, so if it was a cubed plus b cubed, then it would be a plus b, a square minus ab plus b squared. And there's a pattern to this with the signs that you hopefully learned in an algebra course. Okay, so then this factors. We have the limit of x approaching 4. The numerator factors as x minus 4 by x squared plus 4x plus 16. The denominator is still x minus 4. Removing the common factor of x minus 4, I have the limit with x approaching 4 of x squared plus 4x plus 16. And this is now just a polynomial function that's easy enough to work with. So that's 16 plus 16 plus 16, that's 48. So the slope of the tangent line is 48. All right, now we're asked to find the equation of the tangent line. We have the slope, and then we need a point. All right, so what's the point on the curve? Well, we actually, in a sense, already figured out the point. 4 f of 4. Right? The point is 4, 64. So then the equation of the line would be y minus 64 is 48 by x minus 4. And we can take this to a slope-intercept form if we want. I'm not going to show the work for that, but if you wanted to write the slope-intercept form, that's y equals 48x minus 128. You should be able to get to that point using algebra. So this is not really new. We've seen this problem several times. In the very first topic, we used a numerical method. We used tables to approximate the slope. And then when we revisited the problem, I talked about this instantaneous rate of change, and we actually saw a problem like this using limits. All right, now let's go and look at the alternate definition, how another way we can think of this instantaneous rate of change. So instead of thinking of, a to x or a to b, the other approach is to think of our first point here, a, and instead of thinking of the second point with a different variable, instead define the distance from our original point to our second point as maybe h. And then this second point on the curve then has x value of a plus h. Then the slope of the secant line would be f of a plus h minus f of a over the change in x is simply h. Right? Change in y over change in x for slope. And again, this is an average rate of change. And then the slope of the tangent line is then the instantaneous rate of change, which is then the limit with h approaching 0. So if we take that distance between the points and we shrink it down to a very small amount, the limit with h approaching 0 of that same expression, f of a plus h minus f of a over h. All right, so again, an instantaneous rate of change is a limiting process where our distance between the points becomes very small. All right, so let's use that alternate definition to simply, it asks us to find the slope of the tangent line to y equals 3 plus x squared at x equals 5. All right, so at x equals 5, I'll take that as my a value, and I'll take the 3 plus x squared, I'll take that to be my f of x. I'll take that to be my function. Then the slope of the tangent line, that's an instantaneous rate of change. So using the alternate definition, the alternate approach, I will write this as the limit with h approaching 0 of the function at 5 plus h minus the function at 5 divided by h. All right, so now we have to be careful here. How do we evaluate the function at 5 plus h? Wherever we saw the x, we substitute 5 plus h. So this is the limit with h approaching 0. F of 5 plus h would be 3 plus, instead of x, 5 plus h. Instead of x, 5 plus h square. Minus f of 5. All right, so f of 5, all we do here is simply take the function and substitute 5. Nothing new here. F of 5 would be 3 plus 5 square. That's 3 plus 5 is 8. 8 plus 25 is 33 over h. Okay, now we need to expand. If we tried to substitute 0 for h, we would get an indeterminate form here, right? Because notice, if we substituted 0 for h, we would get 3 plus 5 square, which is again 33. So I'd have 33 minus 33 in the numerator, 0 in the denominator, indeterminate form, no good. I've got to do some algebra here. Let's expand the expression in the numerator and see if we can combine any like terms, and hopefully something nice happens. Here's a hint, it does. All right, so let's expand. Limit, h approaching 0. Expanding, I'd have 3 plus 5 plus h. 5 plus h squared, remembering to square a binomial correctly, you get that a squared plus 2ab plus b squared. So that would be 25 plus 10h plus h squared. Minus 33 still in the numerator, divided by h. Now let's look at the like terms. I have 3 plus 5, that's 8. 8 plus 25 is 33. Minus 33, those terms go to 0, right? Those terms go to 0. Right? Those terms that I highlighted in yellow. All right, let's combine what's left. I have a limit with h approaching 0 of, let's see what's left. I have an h plus a 10h. That's an 11h plus h squared over h. So this is a little better, but still indeterminate. Because if I let h equal 0, then that would give me 0 in the numerator, 0 in the denominator, indeterminate form. Let's use some factoring now. This is the limit with h approaching 0 of h times 11 plus h over h. Now I can remove the common factor of h. This is the limit with h approaching 0 of 11 plus h. Now I can substitute 0 for h, and this then becomes 11. And so that's the slope of the tangent. That's the slope of the tangent to y equals 3 plus x squared at x equals 5. All right, so we've seen a couple of exercises here about slopes of tangent lines and using a couple of different approaches. Let's go and look at the position function and to the velocity again. All right, so if we were given a position function, and let's call it s of t, then an average velocity over a to t. All right, well, average velocity, that's congruent to the slope of a secant line. And so that would be s of t minus s of a over t minus a. The average velocity over the interval a to a plus h. Hey, that's similar, just a different notation. That would be s of a plus h minus s of a over h. And again, these are average rates of change. Then if we wanted the instantaneous velocity, we would use a limiting process. So if we were to use the first definition, it would be the limit with t approaching a of s of t minus s of a over t minus a. Or, if we were using the second definition, it would be the limit with h approaching 0 of s of a plus h minus s of a over h. Notice how these are the same notations as the secant line to tangent line problem. We're just using a different type of function. Instead of thinking of a curve and slopes on a curve, now we're thinking of a position function and average velocity versus instantaneous velocity. But notice it's the same ideas. A rock is thrown upward on Mars with an initial velocity of 10 meters per second. Its height in meters after t seconds is given by the function h of t is 10t minus 1.86 t squared. Find the velocity of the rock after 4 seconds. We're given the height. That's a position function, isn't it? This is a position function. Find the velocity of the rock after 4 seconds. We are not given an interval. We're not asked to find an average velocity. We're asked to find the velocity at a specific time. This, we're asked to find an instantaneous velocity. At t equals 4. Let's take that to be our a value. And then we can use either of the approaches. We can say that it's the limit with t approaching 4 of h of t minus h of 4 over t minus 4. That's one approach. Let's follow through with this approach. So then this would be the limit with t approaching 4 of 10, that should be an h of t first, right? H of t minus h of 4. So that would be the limit with t approaching 4 of 10t minus 1.86 t squared. And then I'd have to evaluate h of 4. All right, well, I'm going to go ahead and use my calculator here. H of 4, that would be 10 times 4 minus 1.86 times 4 squared. And that is 10.24 over t minus 4. Now, I know this is an indeterminate form because if I was to substitute 4 in for t, that would give me the same 10.24 in this as the sum of these two terms here. I know it's indeterminate, so then I would have to try to factor this. Gosh, I don't know how to factor that. Okay, let's try the second approach. Maybe the second approach is better. All right, so the second approach would be then, this would be the limit with h approaching 0 of h of 4 plus, let's use a different letter here because I'm using h as the variable name for the function. So let me just change it instead here to s. Let's change my height function. Let me just change the name here for a moment. Let's call this the position function s of t instead. So this would be the limit with h approaching 0 of s of 4 plus h minus s of 4 over h. All right, so now s of 4 plus h, well, that would be, then we would have limit with h approaching 0. So my position function at 4 plus h, that would be 10t. Instead of t, 4 plus h minus 1.86 t squared. Instead of t, 4 plus h squared. Let's not forget the square there. And then minus s of 4, that's again the position function, so minus 10.24 over h. All right, again, let's distribute and combine like terms, and hopefully nice things happen here. Limit with h approaching 0. Let's see, that would give me 40 plus 10h. Now let's see, I'd have minus 1.86. Now the 4 plus h squared here, right? This 4 plus h squared, that is equivalent to 16 plus 8h plus h squared. Right, using a binomial expansion. All right, distributing the minus 1.86 to that, that would be minus, let's see, 1.86 times 16 is minus 29.76. .86 times 8 is minus 14.88 h, and then a minus 1.86 h squared. Still minus 10.24, still over h. Now, combining like terms, 40 minus 29.76, that's 10.24 if I'm not mistaken, minus 10.24. Those terms go to 0. All right, those terms that I just highlighted in blue, those terms go to 0. So let's see what we now have. Limit h approaching 0. I've got a 10h and a minus 14.888. Minus 14.88h. So that's a negative 4.88h minus 1.86h squared over h. I can again then factor out the h. So I have h times negative 4.88 minus 1.86h over h. I can now remove the common factor of h. So I have a limit with h approaching 0 of negative 4.88 minus 1.86h. And now I can finally let h actually approach 0. And then that would give me negative 4.88. So after all that, what can we say? Find the velocity of the rock after 4 seconds. The velocity after 4 seconds is negative 4.88. And what would the units on that be? Well, velocity in meters per second. All right, since we're working in meters, and our time unit is in seconds, so we'd have meters per second. Now, that was a pretty long process for this problem. And we're going to learn that there's a better way, a different way that we can approach this same problem, but we have to learn some more before we get there. So these past couple problems, we were finding the slope of a tangent line, we were finding an instantaneous velocity, but ultimately we were using the same process. And so we are going to give a new name for this concept. The instantaneous rate of change of a function f of x at x equals a, or the slope of the tangent line to f of x at x equals a, or the velocity at x equals a of a position function f of x. These are all represented by the same concept, that limit with x approaching a of f of x minus f of a over x minus a, or the limit with h approaching 0 of f of a plus h minus f of a over h. This new concept, this concept is called the derivative of the function at x equals a. The derivative. This is a really, really important concept in calculus. This concept of a derivative, you're going to use this from now on in your study of calculus, in study of differential equations, in the study of analysis in general. Okay, that's an area of mathematics called analysis. And this concept of the derivative is critical. Notation. The derivative notation, there's a couple of different common notations. One is called the prime notation. So the derivative of f of x at x equals a, I could write f prime of a. Alright, so we put an apostrophe symbol next to the f notation. Another notation we can use is the d notation. So d by dx is a general representation of a derivative with respect to x. And so then if we wanted the derivative of f at x equals a, we could say df dx. And then at x equals a, we use a bar to say evaluate at x equals a. Alright, so this vertical bar is a notation we sometimes use to represent evaluate at. Okay, so these are the two common notations. F prime at a, or df dx evaluated at x equals a. As we continue our study of derivatives, we'll talk a little bit more about notation, but these are the common ones that we'll use right now. Alright, so I'm going to stop this video here now that we've introduced the concept of the derivative and the notation, and I'm going to pick back up in the second video with actual examples of the use of this notation and finding derivatives. I'll see you there.